Hello and welcome to Woven Chemistry. I'm Jean Weaver, and in this video we're going to focus on standardizing a sodium hydroxide solution. More specifically, we're going to focus on your understanding of that procedure. Not whether or not you remember what to do, but if you understand why we do what we do. If you're a little bit shaky on this procedure, then I recommend that you watch my part 1 video where we talk about the what and why of standardizing a solution. All right, let's get started. In this video, we're going to have a series of 5 different questions that are designed to press your understanding. I really encourage you to pause the video, think through the answer, jot down your ideas, and then listen to my answers when you're all done. It's not about remembering my answers, it's about applying your understanding or your knowledge of the procedure and using that knowledge to answer the questions. Okay, so here's the first question. Why is it necessary to standardize a sodium hydroxide solution, but this is generally unnecessary with most other solutions used in titrations? Okay, so take a few minutes and think through your answers and then join me when you're ready. So the answer really stems to this property of sodium hydroxide. It's hygroscopic, which means that it absorbs water from the air, and it actually absorbs a fair amount. So let's say we're planning to make a 0.1 molar solution. We do all of our calculations and we figure that we need 2 grams of sodium hydroxide. So we get out our balance, we scoop out what appears to be exactly 2.000 grams. We're really careful, we use an expensive analytical balance, but the problem is the sample, because of the hygroscopic nature of sodium hydroxide, the sample's not pure. These blue circles represent water vapor that's stuck to the sodium hydroxide. So when we go and we make our solution, we think that we're adding 2 grams to this flask, but in reality we're adding less than 2, which means that our solution concentration is less than 0.1 molar. So because sodium hydroxide is hygroscopic, it's impossible to accurately weigh out a specific quantity of sodium hydroxide, so it's impossible to make a solution of specified concentration. Okay, moving on to question number 2. Sodium hydroxide solutions are often standardized with solid potassium hydrogen phthalate, KHP for short. Why is KHP often stored in a desiccator or dried in an oven before beginning the standardization procedure? Well, really anything can absorb water vapor out of the air. You've probably noticed that maybe when it's been really humid out, maybe the doors in your house stick a little bit, maybe your hair gets a little frizzy, or it just behaves differently when it's humid out versus when it's dry. So KHP can do the same thing, not to the extent that sodium hydroxide does, but we might think, the crystals look like they're dry macroscopically, but microscopically there's a few water particles attached to them. So when we put that on the balance, the balance tells us, oh, you've got exactly 2.000 grams, but in reality, there's contamination with water vapor and we have something a little bit less. So we really want to put dry KHP on there. Well, how do we get it dry? Well, you can put it in an oven, okay, and that will drive the water molecules off through evaporation, or you can store it in a desiccator. And this is kind of a cool device. It's a chamber rather than a device. It contains a substance that has a really strong affinity for water, and it pulls it away from any air or chemicals that are present, and it creates a dry environment, and it leaves your chemicals, specifically your KHP, moisture-free. So the mass of KHP that's used in the calculation needs to accurately reflect the KHP used in the procedure. So that's why we need to dry it to make sure that it's pure. Third question. So KHP must be dissolved in water in order to be neutralized by sodium hydroxide. Does it matter how much water we use, and/or is it important to know how much water is used? So to answer this question, let's think through the whole procedure. So here's our equation. Here's basically what we're going to do. We're going to put sodium hydroxide in a burette, and we're going to drop that down into a flask that contains KHP and phenolphthalein, and we drop it in until this phenolphthalein turns the solution pink. And we need to record the initial and the final volumes. So the measurements that we need are the initial mass of the KHP and the volume of sodium hydroxide used. Okay, let's think through the calculations now and see if water factors in at all. So the first thing we'll do is we'll take these 0.3072 grams of KHP, use the molar mass, and figure out how many moles we have of KHP. Then we'll factor in the reaction ratio, the 1-to-1 reaction ratio, and determine how many moles of sodium hydroxide we have. And then finally, because molarity is moles per liter, we'll use the volume and the moles to calculate the overall molarity. Well, if we look at this, we haven't used the volume of water, the water that we use to dissolve the KHP, that hasn't factored in anywhere. So it doesn't matter. Okay, the volume of water in the KHP solution does not factor into the calculations. So as long as there's enough water to dissolve the KHP, but not so much that the mixing and contact between KHP and the sodium hydroxide is compromised, the amount of water doesn't matter at all. Okay, question number 4. When making solutions, it's always best to use a volumetric flask to improve your accuracy. Why is a volumetric flask not really necessary when making a solution of sodium hydroxide that's going to be standardized? Well, let's think this through again. Here's our calculations. We figure we need 2 grams of sodium hydroxide. Like I said before, we can put what we think to be sodium hydroxide in the balance and weigh it precisely out so it's exactly 2 grams. But because of that hygroscopic nature, we really have less than that. So when we put that sodium hydroxide into the flask, even if we're super careful with the water, we already have this large amount of error with the actual mass of sodium hydroxide added that we can't avoid. So being careful with the water really doesn't matter. Okay, question number 5. When performing a titration, you should always rinse the burette with a few milliliters of liquid before starting. When rinsing a burette that will hold the sodium hydroxide solution, should that liquid be water or the sodium hydroxide solution, or does it really not matter? All right, let's think this through. We've got 2 burettes that we're going to rinse with water or sodium hydroxide. But if you think about it, when you rinse out a glass at home, there's always going to be residual water in that glass because some of it's going to stick perhaps to the sides, okay? Or there's going to be a little bit that just doesn't pour out. And that's going to be the case whether we have water or sodium hydroxide. Okay, so we've got a little bit in here. Now we fill the burettes up with the sodium hydroxide. And we get ready to do the titration, and we have a 1/2 ml as the initial volume for both of them, and then we drain it down. But the problem is, what we should really have, we should drain it down to 12.5, but since in this water rinse burette, that some of the initial initial liquid that's released is really just water and it doesn't do anything for the neutralization reaction, we're going to need to add more. So that means that we're going to have an error in our volume measurement. So in the end, you should always rinse the burette with a solution that will be going into that burette. That way the rinse solution is not going to dilute the contents of the burette and there will be less impact on your overall results. Okay, so I hope these 5 questions have really tested your understanding of this procedure and stretched it, and you've got a much deeper understanding of it as a result. I really encourage you to come back for part 3. In this one, we're going to take a variety of errors that could have happened in a procedure and examine them to figure out if they'll have an impact on the overall calculated concentration, and if they do, will that cause an overestimation or an underestimation? This is definitely higher level thinking and really good practice questions, so I really encourage you to come on back. Okay, as always, thanks for joining me, and I hope to see you again.